Thank you, Dr. Aziz, for the nice introduction today. Yeah, yeah. So, hello everyone. I am Mazharul Islam, and today I will be discussing about content addressable memory, which is a very specialized type of memory that enables high-speed parallel search operation especially in AI hardware. So, throughout this discussion today, I will discuss what content addressable memory is, how that is different from conventional memory like RAM, ROM, and why this has become a crucial part in modern days computing. Not only that, after the I will also discuss about our recent research on content addressable memory based on an emerging device, which is basically 2D material like 2D twisted bilayer graphene. So let's begin our discussion now. So as we all know, from its birth, the downsizing of transistor has brought revolutionary changes of technology that we have witnessed through the last several decades. But as the size of transistor has approached the fundamental physical limit, we have approached concerns that we have never seen before, and those have become so prominent that we have to constantly look for or explore alternative device paradigms. And not only that, we in modern days computing, we also face a famous architecture level bottleneck, which is von Neumann bottleneck, which is basically the separate memory and processing block. For the separation between the memory and processing block, it incurs huge interconnection delays, which we cannot afford in modern days computing. Besides, we all know that memory has not been able to cope up with the constantly increasing speed of the processor, which is known as the memory wall bottleneck. For this reason, researchers are also exploring novel memory device. There is a huge room of improvement in memory end as well. So in this context, the concept of in-memory computing has emerged, where we have the computational element of the processing going place inside the stored memory itself, thus actually reducing the interconnect delay and overall latency to a great extent. This actually has become, in-memory computing has become very popular in recent years due to their several advantages. It has brought revolutionary changes in parallel data processing and rapid data transfer, and it has become a building block in modern days artificial intelligence hardware. Besides, it also tackles the famous memory wall bottleneck, and also it brings the feature of fewer CPU instructions to retrieve data. And for these reasons, a wide variety of device and material platforms have been explored for in-memory computation that can accelerate data-intensive computation nowadays. So any memory that can perform certain degree of computational task in itself is of great interest and have immense prospect in tackling modern days computational challenges. And the memory that we are discussing today, the content addressable memory, is one such kind of memory that has computational capability in itself, which I will discuss now. So, how do we access the storage element or the stored data in a traditional memory? So we actually provide an address in the traditional memory, right? And based on that address, the data at that particular address is accessed. So if, for example, in this figure, if you see, we have to provide the address, and the address is compared, and then we get the data at that particular address. However, this traditional memory like RAM, ROM, they are not well designed for search intensive computation or search. For example, if I want to search search a particular data, not the address, in a conventional memory device, what happens? It actually searches one by one in each of the locations inside the memory block. Until it actually reaches a matching state, until the data that I am searching matches exactly with the data, and then we actually get the address of that particular data. So it requires repetitive fetching from the memory to the comparator block. Given the massive number of data in modern memory block, you can easily imagine how much latency that will bring in computation intensive hardware or search intensive computation. In this context, content addressable memory comes to the rescue because in a content addressable memory, we can search the data in all over the memory block all at once, and quite often even in a single cycle. So it is a great improvement in terms of search latency, and that's why content addressable memory, or CAM, has been widely used in search intensive computations. I will discuss some of the applications now. For example, content addressable memory has been widely used in high-speed networking. So in a networking router, what happens is we provide messages, emails, web pages, all of these things, and we want to send the data to a particular destination. So in our message, the address is encrypted, right? So what happens is that is compared in a lookup table, like the networking routing table, as you can see. And depending on the data, the lookup table actually determines which destination the data has to be transferred. So that's a particular application that where actually CAM has been widely used. For example, if we give a data, the CAM actually compares the data to all the data in the lookup table and selects a particular destination. However, in modern days, artificial intelligence has become a burning topic, and the data computational requirement in artificial intelligence has greatly enhanced, where CAM can be readily impact. For example, in a convolutional neural network like this, which actually detects the image or the type of the vehicle here specifically. So when the trained vehicles are passed through a convolutional neural network, their features are extracted, like their size, their shapes, and these features are stored in a memory, if you can see, like this, an associated memory. So when a new data comes, like this bike at the end, if you can see, that features is extracted in the same convolutional neural network, and that features is compared to all the features that was stored before. But if you have a large amount of data sets, you can easily imagine how much computational latency that will have. In this particular example, we have a conventional memory. So yeah, the extracted feature from the bike will be compared with each of the feature in the conventional memory, which will incur a lot of latency. But if we use a content addressable memory, or CAM, what will happen is once we extract the feature from the new data, the feature will be compared with all the TCAM block all at once in a single cycle. Imagine how much improvement that will bring to the overall classification task. So that is a particular application where actually CAM is being used extensively nowadays. I will talk about the types of content addressable memory now. So there are two major types depending on the functionality of the content addressable memory. One is BCAM, or binary content addressable memory, and another one is TCAM, or ternary content addressable memory. So binary content addressable memory means you can compare binary bits. For example, if you store a data, they're all zeros or ones, and you are comparing it with another data which also have only zeros and ones. That is called binary CAM or BCAM. On the other hand, ternary CAM has another advantage or another feature, which is don't care state or wildcards. For example, in specific applications, we might have some bits that are masked or they're for security purpose. Like if we want to just calculate the last 4 digits of SSN, for example, the other binary bits will be masked. So there has to be a don't care condition sometimes. And in this case, TCAM comes actually into play. So the primary difference between BCAM and TCAM is a don't care state, which we will only get in the TCAM. And since we are actually getting an extra feature in TCAM, it is actually adding some extra complexity and power. We will discuss there are some BCAM and TCAM topologies in our subsequent discussion now. So these are primary structures of BCAM or TCAM in conventional CMOS paradigms. I hope you all are familiar with SRAM memory, right? So today I will discuss about how the content addressable memory is implemented in SRAM paradigm. These are some of the topologies that are commonly found or commonly used in network routing. They are also being used in AI hardware nowadays. For example, if I will discuss the conventional SRAM based CAM. So here you can see that apart from the SRAM bit lines and word lines, we are actually incorporating two extra lines, search lines. If you have a look at it, these search lines will have the search bit. For example, if we have one stored in the in the stored memory, and we want to search one, then what happens is we will give one in the search line and zero in the search line bar, just like a bit line and bit line bar in SRAM. So if both of them matches, for example, if the stored memory is storing one and the search is also one, then they matches, and the match line will have a low resistive path from the match line to the ground. If you can follow the blue arrow here, right? This blue arrow. What that means is when there is a match between the stored memory and the search bit, the match line will get discharged to the ground. So the sequence of searching operation is like this. We will pre-charge the match line first. Then we will provide the search bit in the search line. Now, if the stored memory matches with the search bit, then the match line will gets discharged to the ground. Otherwise, the match line will remain charged. So I hope you get the basic principle of the search operation in this SRAM-based building block of CAM. So this is vice versa. If there is a mismatch, what will happen? So we will pre-charge the match line. We will pre-charge the match line here. This will go high. Then if we provide one here, but the stored bit is 0, there is a mismatch, right? If there is a mismatch, you can see that none of this path, this path, this also, this and this, none of these are actually allow the match line to discharge to the ground, and match line will remain charged. So this way, we can actually detect a matching bits between the search bit and the stored bit. So this is another very commonly used CAM topology, which is NOR binary CAM topology. Why it is called NOR? So if you remember the logic of NOR, the NOR actually, if any one of them actually goes to 1, what happens? In a NOR gate, if one of them goes to 1, the output goes to 0, right? If you remember. So think about it. If we store 1 in this SRAM, then D is basically 1, right? D is basically 1. So, but if we now, if D is 1, D bar is 0. Now, if we give a search bit as 1, what will happen? This is 1 and this is 0. So like the previous one here, when the data matches, when the search bit and stored bit matches, the match line doesn't get discharged. It is quite the opposite, like the previous topology as I discussed. But what happens when they do not match? For example, when they do not match, what will happen is it will be 1 and match line will get discharged, right? So if mismatch happens in a NOR binary NOR CAM topology, then match line will get discharged. And look at this. If all of the CAM cell remains in parallel like this, what will happen? If any of them get discharged, the match line will get discharged, like a NOR gate. So if we want to search a bit stream, we are not actually searching one single bit. We are actually providing bit stream, like 0000. If any one of them get mismatched, the match line will get discharged through this path. Thus, we are actually detecting mismatches here. So, but if all of them matches, the match line will remain in the charged state. So that's how we are actually distinguishing the matched state with the mismatched state. This is another topology, which is basically NAND binary CAM topology. So here what happens is, if there is a match between the stored bit and the search bit, then these two transistors, MD and MD bar, they make sure that this transistor M1 turns on. So if there is a match between SL and D in the figure, then MD and MD bar, these two transistors will work in such a way that M1 transistor will turn on, and this MLN will be connected to MLN plus 1. So are you clear on that? So what will happen is, I'm repeating again, if we stored a bit, let's say 0 or 1, and we search the same bit, then there is a match. And if there is a match, the path will be closed. The transistor M1 will turn on and this path will close. Now, if multiple of these cells are connected in series like this, like a NAND topology, like if you remember how a NAND gate is designed, they are basically connected in series. NMOS are connected in series, right? So if you look at it like NMOS are connected in series. Now, if all of them are connected, what will happen? The match line will get discharged to the ground. You see? So if all my bits, search bit, matches with all my stored bit in a particular row, then we will get 0 at the output, or the match line will get discharged, like a NAND topology. So both of these have their unique advantages and disadvantages. For example, if you remember, if we want to keep a transistor turned on, the minimum voltage it requires is a threshold voltage, right? Across the drain source terminal. So that is one disadvantage that the NAND topology has, because all the transistor has to turn on and they will have a voltage drop, threshold voltage drop across them. Therefore, we will have a disadvantage. However, NAND-based CAM is more cost-friendly and easier to fabricate. This is one conventional topology of ternary CAM. So how here, how the topology was implemented is, we are using two NOR CAM in side by side. That means two storage elements are representing one bit. So far, probably you have only heard of a single bit for single element, right? But it's actually up to us how we represent one bit. We can easily use two storage element, right? Let's say two SRAM, two SRAM for representing one bit. And that is what actually this table summarizes. If you look at it, if you want to store 0, the two SRAM here, one is here and one is here, the two block, and these two block will have 0, 0 or 1, 1. That means it is storing 0. If we storing 1, then it will be 1, 0 or 0, 1. However, if you want to implement the don't care state, which is marked at the X in the table, if you look at it, we will implement it by 1, 1, specifically 1, 1. So that's how we are actually using two SRAM side by side to represent the 0, 1 and don't care state. Now, if any of them actually matches, for example, think about it. Let's say you have stored 1, 1, stored 1, 1. Now you are searching 1, 0. What does it mean? You are searching for 1, but the stored memory is what? Don't care. But you are searching for what? 1. So the first one will match. The second 1, 0 will not be a match, right? The first one will match and second one will not match. Since the first one will match, the left NOR CAM, let me second. The pen is not working for some reason. Yeah. So since we have a match at the left NOR CAM, here it will be a match, but here it will not be a match. Okay. So the left side will match. That's why the match line, the ML will discharge this way. So we are getting like a matching. So you get the point? So we have stored a don't care. That's why we want whatever we give in a search bit. Since the stored bit is don't care, we want what? We want a matching condition. That's how it is implemented. Because the ML can be discharged in both sides, like in the left CAM cell or the right CAM cell, whichever is possible. So that's how we use two cells to actually represent don't care state or implement TCAM, ternary CAM. So there are other platforms where CAM has been implemented as well. For example, magnetic device like MTJ or memory store device. And the principle is pretty similar. As you can see, we can implement the ternary CAM by using two binary CAM side by side, right? So for the interest of time, we will skip this. But keep in mind that if you understand one topology, either in conventional paradigm, like CMOS-based paradigm, or either one of these, like you can easily understand the operating principle of the CAM cells in other technological paradigms, like resistive RAMs or MTJ. So all of these technological platforms have their own set of advantages and disadvantages, but they have some common advantages and disadvantages. Like they all actually provide the feature of fast parallel search and real-time data retrieval. Like you can actually retrieve the data in a single cycle. Therefore, they are reducing the overall CPU overhead. However, all of them have some limitations which researchers are constantly trying to overcome. Like all of them actually incurs high power consumption. Why? Remember, you are accessing all the memory cells in a memory block all at once. So think about it. When you are actually working in a conventional memory, you are not accessing all of them, right? But when you are working with a CAM, you are accessing all the memories in a memory block. That's why actually they are taking high power consumptions. And they also have low storage density and complex and costly design disadvantages. For these reasons, actually, researchers are constantly looking for alternative device paradigms. Also, they are looking for alternative designs or architecture level solutions. Now I will discuss one of our recent research where we have explored a 2D bilayer graphene to design a low power content addressable memory. At first, let me give you a very brief introduction of the device under consideration. So here, the 2D bilayer graphene is sandwiched between a hexagonal boron nitride layers. This particular device have some unique features and advantages. For example, if you provide longitudinal bias current, you get Hall voltage in the transverse direction. That is the perpendicular transverse direction. That means you are providing a current in one direction, but you can read the Hall voltage in a separate terminals. That means we have separate read-write terminals, and it has immense opportunities in a wide variety of applications. If you think about it, like researchers are constantly exploring applications with this device. Another pretty good advantages of this device is this characteristics, as you can see. If you divide the Hall voltage by the current that we provide, you will get the Hall resistance here. You will get the Hall resistance. And as you can see, the Hall resistance is very constant. Like there is not even a single zigzag in the line. Why is that? Because if you look at the value of resistance, what do you see? H by E square. What does it mean? H is Planck's constant and E is what? Electron charge. Both of them are constant. But if I tell you to look at transistor IV characteristics, you will find what? W, L, COX, mu, material and device parameters, everything. But here you will not find it. Both of them are constant. What that means is the resistance, the Hall resistance here does not depend on the device dimension or device mismatches. So if you have process variation, let's say if you want to fabricate one of these devices and you have some process variation or mismatch, the resistances, the Hall resistances will not vary. They will remain intact. They will remain as they are. This is called in physics, which is known as topologically protected Hall resistances. What that means is these only depends on the topological state. They don't depend on the device dimension or device mismatches. So which is a very unique feature that we have taken advantage of. Another unique feature is obviously the non-volatility. Because if you look at the resistance versus current characteristics, you see even at 0 voltage, we get two different resistance, right? One is here and one is here. That means it is non-volatile. Do you remember what volatility means? If we remove the power, the resistance remains there. We don't have, when we turn the power on back again, we can retrieve the whole resistance back again. So this has immense opportunity. Non-volatile devices are a center of attention to the researchers nowadays. So by actually taking advantage of these features, we have designed a non-volatile memory array. This is a selector device. So if you remember, if you want to design an array, you need selector to particularly access a particular device. I will now, for the interest of time, I will just skip this discussion of the selector. So this is our designed non-volatile memory array, as you can see. So what we do is we basically apply current here, and depending on the current and depending on the stored memory, we get Hall voltage at the output at these cells. And remember, they are connected in series. If you just get a look at it, if you connect batteries in series, what happens? Does the voltage add up or get subtracted, or do you have idea? Yeah. Actually, if you connect the positive terminal to the negative terminal of a battery and the positive terminal to the battery to negative terminal of another battery connected in series, and then measure the voltage, you see, measure the voltage at the negative terminal of the first battery and positive terminal of the last battery, all the voltage adds up, right? If you remember. So here we are actually getting Hall voltage in each of these cells. Like this cell has a Hall voltage. This cell has another induced Hall voltage. This cell has another induced Hall voltage. So if you connect them in series, you will get an accumulated Hall voltage at the output, right? So we are providing different current like I1, like I2, like I3, like this. And depending on the currents, we are getting the Hall voltage. Remember? Depending the each of these cells have Hall resistance. If you go back to the slide, each of these cells have two Hall resistance. One is plus and another one is minus. Now, let me ask you, what is voltage related? How is voltage related to current? V equal to IR, right? So remember, we have two resistance. One is plus and one is minus. Now, if we provide positive or negative current, what will happen? If positive matches, we provide positive current and the Hall resistance is positive, what will happen? Plus into plus is plus. We get positive Hall voltage. Similarly, if the Hall resistance is negative, we are also providing negative current. What will happen? Negative into negative, we will still get positive voltage, right? But what happens when those are different? Like we are having positive resistance and negative current, then we will have a negative voltage. Or negative resistance and positive current, we will still have a negative voltage, right? Actually, using this feature, we have designed our CAM in such a way that when those matches, right? CAM is what? CAM is all about matching, right? We are storing zero, we are giving zero. We are storing positive resistance, we are giving positive current. Remember? So we get a positive Hall voltage. We are storing negative and giving negative. Then we will have still a positive Hall voltage. That's how we have actually envisioned our CAM array. And that's how we get a huge positive voltage, large positive voltage at this output, or large negative voltage at this output. And we actually feed it to a comparator sense amplifier here. And that determines if we have detected a matched state or unmatched state. And remember, our resistance is very flat. What that means is our resistance is really constant, which is very tough to achieve, impossible to achieve in conventional CMOS paradigms. Because in CMOS, if you have an array, there will be mismatches. But in here, we will not have that, right? That's why we get a very good result. I will show you the result section now. So the table actually summarizes the content and search. So you see, when we want to store 0, the resistance is negative. When we want to store 1, the resistance is positive. Okay. But when you want to store, when you want to search 0, the bias current is negative. When we want to search 1, the bias current is positive. So based on that, we are getting either positive Hall voltage or negative Hall voltage. You see, these two cases are mismatch and these two cases are match. The first and fourth row is a match and second and third row is a mismatch. So this is the result of our CAM array. And as you can see, we get a positive voltage for matching and negative voltage for mismatch. And depending on the level of mismatch, for example, you will have multiple cells in an array, right? We have shown the result for a 4x4 array. So think about it. In a 4x4 array, how many cells do we have in an array? 4, right? So how many matches or mismatches there can be? Think about it. If we have a 4 cell in an array, we can have 0-bit mismatch, 1-bit mismatch, 2-bit mismatch, 3-bit mismatch, and 4-bit mismatch. So we can have 5 different level of voltage, as you can see, and they are pretty linear to each other. For example, for maximum mismatch, we are getting minimum voltage here. And for the maximum matching, we are getting the maximum voltage, right? And this last figure actually shows the level of matched bits with the voltage that we get. If we put our comparator or in this particular level, what will happen? Below this voltage, all of them will be considered as mismatch. Like remember, our array has a comparator amplifier, like comparator and amplifier, you see? So that comparator actually has a reference voltage. And we have actually selected our reference voltage such that it can detect 1-bit mismatch. So if we put our, one second. So if we put our reference here, like this VREF, do you see VREF? Then only full matching condition will be will give a 1 or high at the output, and all of the mismatches will be given as 0 at the output. So you can easily imagine if you have 4-bit, I have just discussed, we have 5 different level of voltage, right? Because depending on the number of matches and mismatches. So if we have an n-bit operation, we will have n plus number of output voltage. So this is the heat map. Heat map is basically, we have shown the result of a 4x4 array. So if I ask you, how many numbers can we store in a 4-bit number, like 0 to 15, right? 2 to the power 4. So in our stored array, we can store from 0 to 15, and we can search from 0 to 15, right? So this is the stored number, and this is the search number. And as you can see in the diagonal entries, these diagonal entries actually shows the matched numbers, which is basically 9.19 millivolt. And don't get overwhelmed by the millivolt level, because the device that we have discussed today works in cryogenic temperature. It's not a room temperature device. It shows its characteristics below 6 Kelvin. So that's why we are getting very low power. And also the resistance is also very low. That's why the induced Hall voltage is also. So we have also explored ternary cams. So remember, we have two types of cams. One is binary cams and one is ternary cams. So binary cams basically can compare or restore zeros and ones. What is ternary cam? There is an additional type of bit, which is don't care. So we have implemented ternary cams by the same array. However, we have used multiple cells now for representing 1 bit. So in the previous binary cam, if you go back to the array, single cell represents 1 bit. Now for our ternary cam, we cannot do that, right? Because now we have 3 state, 0, 1, and what? Don't care. So that's why we need multiple cells now. So we have used 3 cells, 3 adjacent cells to represent 0, 1, and don't care. And if you look at the left left table, you see how we have represented don't care. Don't care means a positive Hall resistance in cell 1 and cell 3, and negative Hall resistance in the middle. So this was carefully engineered. We have actually engineered in such a way that don't care actually gives us the same result like a matching bit. When we have a don't care, whatever the search bit is, even it is 0 or 1, we get a matched or high voltage at the output. Okay. So these are the results. So this is the don't care condition. So as you can see, for matching, we get 0 volt at the output. For don't care condition, we get 0 volt at the output. This is the summary of the result of the TCAM that we have implemented. So as you can see, when we have matching, like these cases, we have 0 volt at the output, like these cases. And when we have don't care in the stored and searched bit, we get matching. That's how a ternary cam should work, right? So what are the unique advantages of our designed cam array? At first, it is volatile, as I have said, because you can actually turn off the power and retrieve the data afterwards immediately, which this non-volatile memory array has immense applications in a wide variety of AI hardware now. So the Hall resistance is topologically protected. This is I believe, the main advantage of our device. Process variation does not impact the level of Hall voltage that we get. It is constant, right? Well, I have shown you in the previous slides. Therefore, our proposed camera is variation robust, and variation robustness is a very appealing feature of any device nowadays. And it operates in very low power. As I have said, it operates in a cryogenic temperature below 6 Kelvin. So the estimated power it consumes is 1.2 nanowatt approximately per search operation, which is really low considering the other conventional device-based cam. And it is highly scalable. For example, you can easily extend it to larger cameras. For if you want to 64 by 64, you just need 64 cells for the B cam. So the key takeaways from today's discussion is CAM actually provides us the capability of fast parallel search operations. Why? Because it can search a particular data in all the storage block in a single cycle. That is what the primary feature of CAM is. And there are two types of CAM I have discussed in today's class. One is binary CAM and another one is ternary CAM. Ternary CAM has an additional bit state of don't care. And during don't care, we actually implement a matching condition. There is widespread applications of CAMs like high-speed networking and cache tags, and also in modern days AI hardware. There are several challenges of CAMs, especially in SRAM and DRAM-based CAMs, which I have skipped today. You can feel free to actually search for research papers where we'll find a lot of topologies and their corresponding challenges. Researchers are constantly exploring emerging devices, either in room temperature and cryogenic temperatures, for low power, for bringing innovation of low power CAM technology based on emerging devices. And we have discussed one such CAM topology based on 2D material in our today's discussion. So thank you. That's all from me. If you have any question, please feel free to answer. Yeah, thank you.
First of all, one thing that you should take home, must have skipped the slide deliberately, you must have seen, right? After discussing about SRAM, you hopefully understand much better than other memories because we spent considerable time learning about SRAMs. But there was a slide about, hey, can you make spintronic CAM? Can you make ferroelectric CAM, right? So there is a laundry list. But I hope by now you know it's futile to try to go over all of them because they will have unique approaches like his own, idea that he presented. So he decided to present the one that he invented to show you a different flavor of emerging CAM. All right. And by the way, this is not just any design. It was selected as, been mentioned that a best paper in one of the top conferences in the US. So obviously, this has been well appreciated as a good design. Now, what is the take-home message? CAM is a completely different ball game when it comes to memory design, and this is probably gonna gain more attention as we dive deeper into AI systems, as he mentioned. And he kept mentioning search-intensive computing, right? And we are actually heading towards search-intensive computing. Imagine you take a photo of something like a cat, and you're trying to match it with the database that you have. So this database search is being more, basically prevalent everywhere, as you can imagine. When you try to unlock your iPad with your face, there is a database search because it must have stored your face somewhere, right? And not just one image. When you train the system, it takes a bunch of images and it has to test the database every time you have to unlock it. So just forget about the face unlocking, which is a very small scale situation. Imagine Google search. When you search for a phrase in a huge database like that of Google, like, will you just keep, as you mentioned, will you keep searching for every row in its database to find where the data is? That's infeasible, right? So this is the future, and you are getting to know a flavor of the future without, spending too much time in it. And don't worry too much about the quantum animal solidific thing. If you like it, if you understand it, fine. At any point in your career, if you are interested in learning more about this, you're welcome to get in touch with us or read the papers and whatnot. And one thing that I wanted to really, deliver here by bringing him to the class was to show you that most of this new concepts you have to learn by doing, not like it's in the textbook, because they are being invented and deployed in real time. The paper that I mentioned, it was published in 2023 or 24? 23 August.
Yeah.
So towards the end of 2023. And that's when it was discovered and presented. And now it's being taught in class, if you think about it, right? So that's how recent these things are. They're being discovered and being used in real time. So there is no way for us to stay at the cutting edge without getting taking in part in research. All right. With that, I don't have anything else to discuss. Thank you, Mazhar, for taking the time to come here. He wouldn't be able to do it next week, so I decided to bring his lecture today instead of mine. He also discussed briefly about in-memory computing, but we'll basically dive deeper into that in the next class. All right. So next Friday's class will be extremely important. You could stop the recording if you want to.